Have you ever wondered what makes turbo spin echo faster than the standard spin echo sequence? Do you know the real advantages and disadvantages of turbo spin echo in MRI? And what if I tell you that there are just very simple tips and tricks that can help you to master this sequence? So sit tight because today we are going to explore all of this together. But first, everything MRI signal to tune. Dear MRI community, today the topic of our discussion revolves around what is probably the most utilized MR sequence in clinical practice. I'm talking about rapid acquisition with refocused echoes, or also better known as turbo spin echo or fast spin echo. The introduction of TSC sequences has literally revolutionized the MRI world by solving a major problem: slow scan times. In fact, in contrast to the standard spin echo sequence, TSC enables what we can call rapid imaging. And this is possible thanks to the peculiar pulse structure that characterized TSC. After a single 90-degree excitation pulse, TSC employs multiple 180 refocusing pulses in quick succession. Each pulse creates an echo, forming what we can call the echo train. The number of echoes per train is called echo train length. And you can think about it in this way: more echoes translate into faster scan times. But why does this happen? The reason is each echo fills a different line of the case space, meaning the matrix where the raw data of our MR image are stored. While traditional spin echo fills one line per repetition time, TSC fills many lines in just a single TR. And right because of this, our scan time in MRI now can be cut significantly. As we mentioned earlier, TSC is widely used nowadays in clinical practice, from neuro to MSK to cardiac imaging as well, and the use is often associated with the achievement of flexible image contrast. Depending on the TR and TE values we input on our scanner, we can obtain TSC sequence which will be more T1 weighted, T2 weighted, or perhaps PD weighted. So we touched on this briefly, but what are the advantages of using TSC sequences in MRI? The first, as we said, it is achieving faster scan times. And for those of you working in MRI routinely, we know how crucial this can be. And think about dealing with uncooperative patients, for example, like pediatric cases or those with neurological conditions. We cannot expect them to stay still for prolonged scan times. Additionally, healthcare systems in many countries are facing a huge backlog in terms of MR service provision, so speed has become a top priority in MR technology. Another advantage is the high sensitivity and robustness that characterized TSC sequences. Just to throw some example, we know the turbo spin echo is particularly valuable for evaluating the CSF in neuro MRI, for example, and T2 sequences, T2 TSCs can be particularly useful, especially if combined with fat suppression when it comes to detecting edema or perhaps any type of tears when it comes to MSK imaging. MR users also appreciate TSC robustness against specific type of artifact. Let's compare TSC to gradient echo to reduce metal-induced artifact. TSC, especially when combined with higher bandwidth and metal artifact reduction techniques, is far more reliable for reducing artifacts in patients with implants compared to other type of sequences like gradient echo. This leads us to advantage number 3, which is versatility. As mentioned, TSC is used in a wide range of clinical applications. We use it routinely in spine imaging, we use it for brain studies, we use it for gynae examinations, and this makes it adaptable to diverse clinical questions. But for those of you that are a little bit more seasoned MR radiographer, you know it. MRI always involve a trade-off. Every benefit has potential drawbacks, and TSC, trust me, is no exception. The first major disadvantage we can touch on is linked to the specific absorption rate, the SAR. The repeated 180 refocusing pulses in rapid succession increases the energy deposition, and this isn't just a safety concern for patients, but it can also create SAR conflicts for radiographers, especially when working at 3 Tesla or higher. Another limitation is the presence of blurring artifacts. The longer the echo train and the greater will be the blurring on our image. This means we must be particularly careful when it comes to dealing with parameters like the turbo factor. Pushing it too high might speed up the scan, but at the same time might also degrade the image quality. Lastly, while TSC's insensitivity to magnetic susceptibility artifacts is often a strength, it becomes like a sort of weakness when we need to detect calcifications or microblades. So for this, gradient echo remains the go-to. So acknowledging that there are pros and cons, how do we optimize turbo-spin echo in our daily practice? Let's find it out together. My first tip, as already discussed on our focus on the turbo factor, is to shorten the echo train length specifically for TT weighted sequences. While there is a tendency to increase this parameter clinically, try to aim for a value between 14 to 20 echoes in order to minimize blurring. Remember, scan time reduction with turbo factor doesn't follow a linear pattern. Increasing the echo train length and SAR limits might lead to the selection of longer repetition times, and this will overall increase the scan time. Next, while TSC offers incredible flexibility for different weightings, always consider the magnetic field strength you're working with. The manipulation of certain parameters have a different impact on the image quality according to the magnetic field strength. For example, reducing the flip angle at 3 Tesla can improve the gray-white matter contrast in brain imaging, and this is an effect which is less pronounced at 1.5 Tesla. Finally, as we already touched on, in our aging population, TSC role in metal artifact reduction is literally a blessing. However, do not rely solely on the bandwidth, but try to combine TSC with software like the VAT or CMAC in order to tackle in-plane and potentially through-plane distortions. CMAC, for instance, dramatically improves the image quality near the metal implant by reducing both in-plane and through-plane distortion. And this is a topic we covered very recently in our webinar, completely focused on Mars sequences. To summarize, TSC is probably one of the best tools in our MRI arsenal. It is fast, it is sensitive, it is robust, and this is particularly the case when it comes to metal artifacts. It is also arguably the most versatile sequence out there. But it requires careful balancing, including careful SAR management, echo train length potential adjustments in order to avoid image blurring, and also knowing when to switch or to include another sequence in the clinical protocol, like for instance for gradient echo for microblades or calcifications. But I'm sure there are still a lot of things we can add to this list, so guys, make sure you drop your TSC optimization tips here in the comments. If you enjoyed this content, make sure you subscribe to our YouTube channel and you follow Everything MRI on all our social media platforms. As usual, I hope you find this video useful, and I will see you next time.